This is a video to help you with doing conditional probability questions and independent event probability questions. So let's go to the probability chapter and let's check this section here, calculating probabilities for intersections. So we discussed this in class. Two events are called independent if and only if the probability of event B, two events A and B are called independent if and only if the probability of event B is not influenced or changed by the occurrence of event A. And we saw this example of colorblindness. We saw that these two events A and B are not independent because if somebody is male, that affects the likelihood that they're going to be colorblind. So those are not independent. On the other hand, we saw this example about tossing dice. We said observing a 2 on the first toss, and observing a 2 on the second die or the second toss, those would be independent because we don't think that what happens on the first die has any effect of what happens on the second die. So those are called independent. And then we saw this new notation with this vertical bar here. And I said that that does not mean divide, has nothing to do with divide. It just is a shorthand way for writing something like this. So what does this say? A here is getting a 2 on the first toss, and B is getting a 2 on the second toss. And this says what? The probability of B given that A occurred. So the probability of getting a 2 on the second toss given that we got a B on the second toss on A. So that's 1/6. It doesn't matter. And then let's read this one. Probability of B given that A did not occur is also 1/6. So it doesn't matter whether A occurs or it doesn't occur. The probability is 1/6. So that's why we say that they are independent. But anyway, this notation is just a shorthand for this word given. So instead of saying B given A, we write, instead of saying A given B, we write A/B. That's called the conditional probability of A given B. The conditional probability of A given that B has occurred. So we showed this in class, and I made an argument. This was the sample space S, and here we have an event B, and here we have an event A, and here we're asking what's the probability of A given B, and we saw that that was given B means that we must be in the shaded region here. So the only part of A that can occur is this part of A. So we talk about the new sample space as B, and then the size of A that can occur is only the part of A that is in B. So only A intersect B can occur, and that's within the event B. So the probability of that, we said, was we had n of B, forget about this piece here and this piece here, we had n of B on the bottom and n of A intersect B on the top. And then I said divide both sides by n of S, and you end up with this, the probability of A intersect B divided by the probability of B. So that's the probability of A given B. So actually, we make this argument here that the probability of A given B is equal to this, but we actually define this to mean this. So the probability of A given B equals the probability of A intersect B over the probability of B. But we gave this reason for why we make this definition of what the probability of A given B is, and we gave this argument here for why we make this definition. But this is the definition. So here we say the probability of A given B is this over this. That's what we just argued. But of course you can just bring the probability of B over to this side, so you get this. So we can write this, or of course we can write it like this. So just putting this on the other side. So we get this equals that. And that's what they have here. Actually, they have B given A here, so just they put A here. And anyway, it's the same thing. You can easily see that that is the same as that. Just renaming A and B. So we should remember that the definition of A slash B, the probability of A slash B, or A given B, is this. You have to commit this to memory, but you should also remember how simple it was to argue that that's what it should be, using what we wrote on the blackboard. And then you should also remember this form of it, because we asked earlier, or I should say we had this from before. We said we had an expression for the probability of A union B. We had this, which we explained earlier. And then we said, well, is there some expression for intersection? And now we have one expression for intersection. Actually, we're going to write this, we're going to come up with another expression for intersection, but that's going to be for a special case. This is always true. Same thing with this. We can come up with a special rule for this one in a special case, which is a little simpler than this one, and the same thing here. We can come up with a special case for this one, which will be slightly simpler. But anyway, right now we have an expression for the probability of A intersect B, and another one for the probability of A union B. You need to understand and remember both of these. So here they call this the general multiplication rule. Okay, so this is it, which can also be written like this. So instead of BA, we can have AB. Then we'd have A here, we have B here. Okay, let's see this example. So they talk about a color preference experiment. 8 toys are placed in a container. The toys are identical except for color. 2 are red and 6 are green. A child is asked to choose 2 toys at random. What is the probability that the child chooses the 2 red toys? So what does this have to do with what we just learned? So they say use a tree diagram as shown in figure 412 and define the following events. So here's the 412. So we have, the first choice, the child could choose red or green, and these are the probabilities of choosing red and green. Now if they chose red here, then there's only one more red left, so the probability of choosing red is only 1, and there's only 7 toys left, so it's 1 out of 7. And the alternative green is 6 out of 7, and this is 2 out of 7 and 5 out of 7. You can check that yourself. So we're going to define 2 events. Red toys chosen and a green toy is chosen. And we want to know what's the probability that they choose 2 red. So what does 2 red have to do with this R? Sorry about that. Every time I select something here, this shows up. So what does 2 red have to do with this R? So 2 red means red on the first and red on the second. And the word I just used is and. 2 red means red on the first and red on the second. So and means intersection. So we can write this as red on the first intersect red on the second. But we said we have a rule for the intersection here. So the probability of A intersect B is this and this. So the probability of red intersect red, red on the first intersect red on the second is the probability, let's do it the other way around. This is red on the second and red on the first. You could do it the other way, but it doesn't work very well here. So red on the second and red on the first. This is the probability of red on the first. and then times the probability of red on the second given red on the first. So what is this probability? The probability of red on the second given red on the first. Well, we already did that. Red on the second given red on the first is this one, 1/7. So it's 1/7 here, or 1/7 here, and then this one is the probability of red on the first, where we already did that as well, and that was 2/8. 2/8. So it's this times this, and that comes from this rule, the intersection rule, okay, which is here, the intersection rule here. Okay, so we get this answer, which they do here, same thing that we did here. They do it here, where they get this times this, which is 1/28. That's the, and they point out that this solution was only possible because we knew the probability of red on the second given red on the first, because we required that. If you don't know the conditional probability of A given B, you may be able to calculate it using the multiplication rule in a slightly different form. Just rearrange the terms in the multiplication rule. So they didn't start with this definition, but they say you can get to this definition just by rearranging the terms. So what they're saying is, they started with this, and then they say it's easy to go to here. We started with this and said it's easy to go to here. Anyway, they're both the same. So this says the conditional probability of an event B given an event A is this over this, as long as the bottom part is not 0. If the bottom part is 0, we have some problem. Okay, let's continue with this colorblindness example. So they say, suppose that in the general population, 51% of men are colorblind and 49% of women are colorblind, and that the proportion of colorblind men and women are shown in the following probability table. So we have here we have 51% of men. Oh, I'm sorry, I read this wrong, didn't I? I just skipped through this too quickly. It says the population is 51% for men and 49% for women. Okay, let's continue with the color blindness example. So they say, suppose that in the general population, 51% are men and 49% are women, and that the proportion of color blindness between men and women are shown here. So men, 4% are colorblind, and women, 0.2% are colorblind. So we can see that if we add these two up, this is the total percentage of colorblind people in that population, and this is the percentage of non-colorblind people in that population. And here, when we add these two, we get colorblind men and non-colorblind men, we get 51%, and here we get 49% for women. Now they say, if a person is drawn at random from this population and is found to be a man, what is the probability that the man is colorblind? So we're going to, here we have, we're calling event B as what? That we've drawn at random a man, and event A is that the person or the man that we've drawn is colorblind. So what we're asking in this question, where this question mark occurs, is given that the person is a man, given B, what's the probability of A? Given B, what's the probability of A? Now we just use the definition that we just had up here, and we get it's A intersect B on the top, probability, and B on the bottom, probability. So what's the probability of A intersect B? What does A intersect B mean? It means A and B. So what does that mean? that means that the person is colorblind and a man. So that is man, and colorblind is 0.04. And what goes on the bottom? The probability of being, B is man. Probability of man is 51%, so it's this over this, which is that. So that's the answer to this question. Okay, now they ask a different question. What's the probability of being colorblind given that it's a female? So that would be the probability of being colorblind given female is what? B means male, so B complement means not male. The opposite of B, or the complement of B. So now we just use the same definition again, but we use B complement here. So B complement is interpreted as being female. So the probability of female in the population is 49%. The probability of A intersect B complement is here. So it's that over that, which is this. So given that it's a female, it's this percentage. Given that it's a male, it's this percentage. So it's a lot higher for men than it is for women, right? It's how much higher? Let's see. It's a lot higher. It's nearly 16 times higher, right? Or it is 60. It's probably even more than 16 times higher. Did I get that right? I think so. Yeah. So it's a lot more likely to be colorblind if you're a man than it is if you're a woman. It's like 16 times more. Okay, also now they point out that being colorblind given B and being colorblind given the opposite of B are not the same. That is, being colorblind depends on whether B occurs or not. So that means that A and B are not, it means that A and B are not independent, right? They are called dependent here. Okay? And here, they say when two events are independent, that is, if the probability of event A, the probability of the event B is the same whether or not A has occurred, then event A does not affect event B. And that means that the probability of B given A is just equal to the probability of B. It doesn't matter whether A occurs. It doesn't change our calculation of the probability of B. So this is our formula for when we call two events independent. Okay, so now we have a formula for it. Okay, and that is here. The two events A and B are called independent if the probability of B given A equals the probability of B. Okay, that is, it doesn't matter that A has occurred. The probability of B given A is just the same as the probability of B. So now they go back to this. Okay, so let's take this. Can I copy this? I don't think so. Let's see, copy, no. Here. No, I can't copy it. Okay, I have to write it. So let's see, probability of B given A equals probability of B. Well, on this screen, it's instead of B given A, it's more convenient for me to write this one since this is what I have here. So I'm going to say that that by independent, let's see, by independent, I mean that the probability of A given B just equals the probability of A. It doesn't matter that we know B. The calculation is just the probability of A. Okay, now with that rule, we can get a new version of this one. But this new version is going to be true when this is true, because I'm going to use this in it. But that means this new version is only going to be true when the two events are independent, when A and B are independent. So I'm going to put a new rule here. I can replace this with this when they're independent, so I can take away this and put in this. Let me do that. Okay, so now we have the easier rule for intersection. The probability of A intersect B is just the probability of A times the probability of B, or either order is okay. But this is only true when they're independent, when A and B are independent. So if they're independent, we get this easier rule for intersection. But that's actually very rare that two events in reality, when you're talking about dice or coins or something like that, things are independent. That's easy to see. But actually for most events, like if you're looking at medical or social science or whatever the events are, oftentimes they're not independent. So it's pretty unusual that events are actually independent. Anyway, going back to here, they say can now be simplified like this. So this, you can remember this as for intersection, you can change it to multiplication, but only when the two events A and B are independent. And this can easily be shown for more than just A and B. If you have A intersect B intersect C, if they're all independent, you get something like this. Okay, so coin tosses at football games. So sometimes in football, I guess American football, at the beginning of the game, they toss a coin, or maybe they toss 3 coins I don't know what they're deciding, but they're deciding something. Or here, a football team is involved in 2 overtime periods during a given game, so that there are 3. Anyway, for some reason, we're tossing a coin 3 times. So if the coin is fair, as the question is, if the coin is fair, what is the probability that you lose all 3 tosses? So I guess lose means you get tails each time, or no, sorry, win and lose. So you can define A, that you lose on the first toss, B, that you lose on the second toss, and C, that you lose on the third toss. So you're not saying how you get lose. I mean, does it mean you get a tail or a head? They're not saying, but you're either going to win or lose. So we can talk about it in those terms. Since the tosses are independent, and because the probability of win equals the probability of lose equals 0.5 for any of the 3 tosses, we want to know the probability of A intersect B intersect C, that all 3 of these occur. And since they're all independent, we can write it like this. And so we can write it, but these are each 0.5. So the probability that this happens is 0.125, which is also equal to 1/8, 1 out of 8. So our original definition for independence was here, but they say sometimes this is not as easy to use as this. So we can use this as the definition of independence also, and then from here we also get this, or we can use this as the definition, and from here we saw that we got this. So either one is okay to use as the definition of independence. So they say, how can you check to see if 2 events are independent or dependent? The easiest way is to redefine the concept of independence in a more formal way. So here they're going to use with the second form. The probability of A intersect B equals the probability of A times the probability of B. That's what we're going to define to mean independent. They say you can also use this, like we just said. If this is not true, or if this is not true, then the events are called dependent. But if this is true, or this is true, they're called independent. So here you can check, you can use the definition to check whether these 2 events are independent or not. So I'll let you read through this yourself. You can also go through this one, refer to these. This is a child in college, no child in college, too high. I think we talked about this in class. Are events D and A independent? So D is child in college. Is that independent of the event of thinking that the price is too high? So I'll let you read through this to see whether these two events are independent or not. So if someone thinks that someone has a child in college, does that affect whether they think that the tuition is too high or not? You might think that maybe it does, right? Because if you have a child in college, you're going to be kind of very sensitive to the tuition, right? Whereas if you don't have a child in college, you might not be thinking about it that much, so you might not care that it's high. So you might think that these are going to be dependent, but let's do the actual calculation to see the way it actually turns out. Okay, next is this review of the concept of mutually exclusive compared to the concept of independent, because it's somehow they seem to be related, or you might even think that they're the same. You might even get confused and think that they're the same. They're definitely not the same. I used to make the mistake, unfortunately, for many years of saying they had nothing to do with each other, but that's not true. So they do have something to do with each other. So I'm quite embarrassed or ashamed to say that I didn't realize they're related. But anyway, they are somewhat related. So let's look. So remember, well, we just talked about independent here. So two events are called independent when the probability of A intersect B equals the probability of A times the probability of B. Okay, so that's independent. Now let's review what is mutually exclusive or disjoint. Remember, we said that they can't happen at the same time, or that their intersection is empty. Right? We said that when the intersection of A and B is empty, so they're disjoint, then that means they're mutually exclusive. Okay? So that means the probability of A intersect B equals 0. But going back to wherever we had it here, that means this part here, when things are mutually exclusive, this disappears. So all we have are these two equals that. So this says that when they're mutually exclusive, union becomes plus, and just before we said that when they're independent, intersection becomes times. So these are special cases of the rules in general. Okay, so we have this and this. So anyway, that's what we mean by mutually exclusive. So this is equal to 0, or this equals only this plus this. So going back here, when two events are mutually exclusive or disjoint, the probability of A intersect B equals 0, and the probability of A union B, therefore, we don't have that third term here, and we just get this. Okay, so now we've reviewed those two concepts. Now, here's the argument. When two events are mutually exclusive or disjoint, that means here, this part, that means, sorry, here, the intersection is 0. When two events are mutually exclusive or disjoint, they cannot both happen together when the experiment is performed, because they're disjoint. Once event B has occurred, event A cannot occur. So, and here's the part I never picked up on, the probability of A given B has to equal 0 in that case. So if they're disjoint, then the probability of A given B is 0, because given B means A can't happen. The occurrence of the occurrence of event B certainly affects the probability that A can occur, right? So if B happens, it definitely has an effect on A. In fact, the probability of A in that case is 0. Okay? So therefore, A and B are definitely not independent. They say, therefore, mutually exclusive events must be dependent. Okay, so please remember that. Okay, and then they do another example here. 2 cards are drawn from a deck of 52 cards. Calculate the probability that the draw includes an ace and a 10. And I'll let you go through that yourself. Then reviewing the probability rules, we have the addition rule. That's the general rule for union. And if they're mutually exclusive, the general rule becomes simpler like this. And rules for complements. The probability of A complement is 1 minus the probability of A. Multiplication rule is a rule for intersection. Looks like this. Can also be written like this. And if they're independent, it becomes simpler. It just looks like this. And they have some exercises for you to do. So you should go through some of these. And that's all for now.